Within this world of mechanisms, we want to talk about rate determining steps. So when you're dealing with a reaction mechanism, you're saying you have a sequence of chemical reactions that have to occur, right? You have all of your elementary steps, and they have to happen one after the other. And each of them depends on a collision. Each of them has a collision with an associated activation energy. There are steric concerns, orientational dependence, all that good stuff. And so one of them is going to be the slowest. One of them will be the slow step. And we call that the rate determining step. You also hear it referred to as rate limiting. So that word determining, what you are saying is that the overall rate of the entire overall chemical reaction is determined by the rate of that slow elementary step that's in the mechanism. So this is similar to anything else where you have a flow of material through steps. This right here is the slow step in this traffic system. You have a merge onto the system, you have a truck that's broken down in the right lane, people are having to go around, and you're having all these issues. So that is the slow part of the process. Back here, there's no reason for traffic to be moving slowly there. Theoretically, that should be a fast portion of the process, but it is slowed down because it's behind the rate determining step. So yes, there are no obstacles there. There's no broken down trucks, no merge required, but it is still happening slowly because it's behind the slow step. After the slow step, you're home free, right? Once you make it through the merge, once you make it past whatever's causing the backup, you just fly, right? It doesn't matter. Things can go fast, but it's important to note that you aren't slowed down by the rate determining step once you are past that rate determining step. Each elementary step corresponds to some sort of collision or molecular process, and as a result, each one will have its own activation energy. And whatever the highest activation barrier is going to be your rate determining step. It could be first. You could have that the first step is really high, and so you think you kind of like go up enough energy, but then you just roll back down the hill, right? So that one doesn't work, and then say again, a little closer, but you roll back down the hill, doesn't work. Eventually, you will have a collision that has enough energy to make it over this first hill. If it has enough energy to make it over the first hill, it will speed up and then easily make it over that next hill, right? You have enough energy. Those molecules are moving fast enough after that first collision. Basically, they come out of that first collision with a lot of energy. So that second collision is going to be easy, right? It is any molecule that can make it through the first collision is going to have enough energy to make it through that second collision because it already had a lot of energy because it made it over that first step. And so it's just going to fly past that second step and it's going to go well past it. Conversely, if the first step is easy, so say, it's easy to make it over the first one, you boom, barely you make it over that, but then you can't make it over the second step, you roll back down, boo, 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 kind of going back and forth, right? So that first step, it doesn't matter if the first step's easy. This idea of this first step being real fast, you get over real fast, but then you roll back down, right? It doesn't make it over. And so what you really need to do is something that is really fast for the first one and then can make it over the second one. Because you really need to care about making it over that second barrier. So wherever the highest barrier is going to be rate determining. Either you need enough, it doesn't matter if you can make it over the first low barrier, or if you can make it over the first high, anything after that high peak is going to be easy to get over. So if we actually look at the NO2 and CO reaction that I mentioned at the beginning of reaction mechanisms, the mechanism here is two NO2 molecules collide, make NO3 and NO, and then the CO molecule reacts with that NO3 to make CO2 and NO2. So these are your rate steps. And we have a kind of relative depiction of the reaction barriers for those two steps. We can see that the barrier for 1 is much higher than the barrier for 2. What that means is that the reaction constant, the rate constant, K1, is much lower than the rate constant for reaction 2. That K2 is going to be much higher. The K2 is much faster. So what that means is that your first step is slow and your second step is fast. Or we could also say that the first step is rate determining. But generally, whenever we call a step slow, it is relative. We're not necessarily saying that everything else is very fast or anything like that, or that it is even a slow step. It is just the slowest of this reaction mechanism. So if you had, say, 7 steps in your reaction mechanism, one has to be the slowest step, and we call it the slow step. Because that is the slow step, because it is rate determining, the overall rate of the process is just equal to the rate of the first step. That is what we mean by rate determining. You can just say the overall rate is equal to the rate for the first step, and you can just, because the first step is elementary, you can get the order from that reaction coefficient. So that is just a collision of 2 NO2 molecules, so it's going to be second order. That comes from that 2 that's right there. This also tells us why the CO is 0th order. So increasing the amount of CO doesn't increase the rate of the reaction because CO shows up after the rate determining step. That's part of the fast step. So if you put more CO, the second step will get faster, which is great. It is there. The second step will get faster. But the thing is, the second step was already fast. So making the second step faster will not be noticeable, right? You won't notice it because it was already the fast step. The slow step is just making the NO3 for the CO to react with, right? You have to make this as an intermediate that then shows up in the second reaction. So that first step is rate determining. That is what's slow. You're not low on carbon monoxide. That's not your problem. It's reaction. The problem is getting that first step to happen. So that's why CO is 0th order. It's in the reaction mechanism, but it's in the fast part after the rate determining step. Rate determining step is not always first. We have a reaction mechanism for the overall process is O2 plus 2NO gives me 2NO2. First, an NO reacts with the O2 to make NO3, and then NO plus NO3 gives me 2NO2. And if we look at the reaction schematic for the reaction energy, I can see that that first barrier is relatively short, second barrier is quite tall, and so I would then say that the K1 is probably going to be a lot higher than K2. Just because that first EA1 is much shorter than EA2, which tells me that the first rate is fast and the second step is slow. That's my slow step. So because the second step is slow, I can still use rate determining. Rate is equal to rate 2. Okay, that works. Rate is equal to rate 2. That is my rate determining step, so I can just use that right there. But you will note that NO3 shows up right in there. And NO3 is then what it actually matters. And that makes sense. NO3 is a reactant in the second step. But you will also note that NO3 does not show up in the overall reaction. It is an intermediate. So it is true, the overall rate is based on the concentration of NO3. NO3 is a highly reactive molecule that you are not putting in as your reactant mixture. So we don't want that to show up in our rate law. Right? What we want is a rate law expression that is based off actual reactant concentrations, because that's how you actually set up your reaction mixture. So we're going to need to do some algebra tricks, some algebra work to get rid of that NO3, to figure out what the concentration of NO3 is based on the concentrations of reactant species. So what we can do is we can kind of look into what's going on here. We know that this first step is fast, and it happens relatively quickly. Most importantly, it happens relatively quickly relative to that second step. And so what that means is it just starts happening, right? The overall process isn't happening, but you are forming NO3. You are just starting to react NO and O2. So we have our NO is right here, the red and the blue, and the O2 will make it a vertical orientation, is the 2 red oxygens. And so they're combining to give the NO3, and this reaction does just start to happen, and the concentration of NO3 starts to increase. And so our issue is what happens with that NO3. The NO3 has a couple different changes that it can do. It has 2 possibilities. It can undergo the second step, and the second step that we've identified right here. It could interact, it could collide with another NO molecule, and it could undergo the change, the slow step that we're interested in, make our products. Or it could fall apart. It could do the reverse of the first step. And that's relatively fast, right? That would be the barrier is just right here to get up to that right there. That's pretty easy. That's a really short step. So that ends up also being fast. And so it starts to happen. This idea that we're kind of broaching is the concept of microscopic reversibility. So when we talk about reactions, we say that these molecules are reactants and this molecule is going to be the product, and this is the reaction, this is the direction that the change happens in. But atoms don't care. Atoms can just change anyway. And if there is some sort of elementary step that can happen where there is a collision of atoms that causes a change, the opposite process has to be possible. So if you are saying that this NO molecule can come in and collide with these O molecules, this O molecule, and it can form this new interaction where you have, say, the N molecule forming bonds to 3 different O's, then it's also possible that that can happen in the opposite direction, where maybe these 2 O molecules come together and form a bond, and you break, leading to the formation of this O2. Right? And this has to be possible. Anything that can happen in the forward direction can also happen in the reverse direction, right? The microscopic reversibility, the process of atomic bonds rearranging can happen in the forward direction or the reverse direction. And we can define a rate law for either direction because they're both elementary. So we're going to add F for the forward process and R for the reverse process. And then the coefficients in these processes just become the orders up here, right? The ones or the whatever it is. It's important to note this idea of forward and reverse is entirely arbitrary. This is something we came up with. Molecules don't know I'm a reactant, I'm going to become a product. This is just kind of shorthand that we're going to use, but that's fine because we're chemists. We're trying to control this chemical reaction. So we're going to call one the forward process and one the reverse process. All right, so these will both be happening, right? So we've mixed our reactants. I have the horizontal is the NO, the vertical is the O2, and they're going to start reacting, right? So they're going to start reacting and they're going to form some NO3. And it's just going to keep going because it's a relatively fast process, right? But the thing is, that rate of the forward process is based around my concentration of NO and O2. As the reaction starts to happen, those concentrations go down, meaning that this rate is decreasing. The forward rate is going to slow down. That reverse rate, the undoing of that process, is based on the concentration of NO3, which I was just increasing, which means that that rate is going to increase. So they undergo reactions. The NO3 molecules start to fall apart. At the same time, the forward reaction can still happen. So these are, I have billions of molecules that are all here together, and these reactions can happen in both directions at the same time. Certain atoms will go into one kind of configuration with the separate molecules or the combined product molecules, and these can go back and forth. Eventually, we will reach a state where the forward reaction is happening at the same rate as the reverse reaction. Basically what that means is you are creating this NO3 at the same rate, you're going this direction, you're forming NO3 at the same rate that you're destroying the NO3, that you're going backwards. And so what would end up happening is all of your concentrations would become the same, right? They just stop changing. The individual atoms still keep reacting, but you overall have a constant concentration, and we call this equilibrium. So when we have our first reaction being fast, that first reaction is in equilibrium. So it's going, both of the processes are happening, not just the forward, but also the reverse. And we can use that to determine the overall rate law, to get an overall rate law for this reaction that's only based on reactant concentrations. Let's see what that looks like. Okay, so when we have a situation where the first step is fast and the second step is slow. So we've seen that when whatever step is slow, we know that the overall rate, so my reaction rate, is going to be equal to rate 2, whatever the rate of that slow step is. And then because this is a step of a mechanism, that's elementary, so it's going to be NO and NO3. And so where the problem comes in, especially this always happens when a second step is slow, is that NO3 is an intermediate. So NO3 is an intermediate, so I don't want to say the overall rate is dependent on the concentration of an intermediate. That is true. The actual rate of the reaction depends on the concentration of this intermediate, this thing that is formed in the first step and then consumed in the second step. The reason why I don't want that for my overall rate reaction is I don't have control over the NO, I don't have direct control over the NO3 concentration. The whole purpose of a rate law is to give us guidance as to how to control a rate, to kind of make suggestions as to this is what you could do to increase the rate of a reaction. And if NO3 is an intermediate, we're not adding it to the mixture, right? That's not something we're choosing. That's something that just happens as a result of how these reactions all flow together. All these steps all flow together. So that's where we want to use the fact that this first step is fast. So because the first step is fast, this is the idea where we go to equilibrium. And what that idea of equilibrium means is that for this rate 1, that the rate 1 forward is equal to the rate 1 reverse. Right? We have this idea that our barrier, our energy diagram looks like this. And so what's going to end up happening is you'd have some of the forward reaction happening, but then at the same time, you also can have these backwards reactions happening. Right? Just because we're saying NO becomes O2, NO plus O2 becomes NO3, NO3 can also change to go the other way. These are elementary steps. You're just rearranging bonds. Atoms don't have brains, so they can't pick a direction to go. They can just change in these ways. So we can define our forward and reverse. This is the rate law for the first forward reaction. Throw in F for forward. NO O2 is equal to K1 reverse times the concentration of NO3. If the forward reaction is elementary, backwards reaction also has to be elementary, so we can come up with that rate law. And then basically the whole point of doing this is we just have established an algebraic relationship, and we can see that the concentration of NO3 shows up in that relationship. So what we can just do is we can rearrange this equation, and we get K1F divided by K1R times the concentration of NO times the concentration of O2 is equal to the concentration of NO3. So what we've just done is we've gotten a concentration, we've gotten an algebraic representation for what the concentration of NO3 will be based off these concentrations. Right? So what we can do is we can plug that into here. So let's go to the second page now. We had this idea that rate was going to be equal to, we know the second step because the second step is slow, times NO3. And what I'm going to do is I get K2 NO, and then in here I'm going to put, basically I'm going to substitute in everything that I got from the previous representation. What the concentration of this intermediate was based off those reactant concentrations. And so these are things that I can control now. It makes sense, the more of the reactants I put in, the more of the intermediate I'm going to have. The K1F, that'd be the rate constant of the forward process for this first step. The faster that is, the higher the concentration of NO3 is. The faster the reverse is, the undoing of the NO3. If that's really big, you're dividing by a big number, you're going to decrease it. So what we can do now is we can take this and basically we can rearrange these things. One of the things we can see, I have NO concentration showing up twice. I can group all the K's together. K2, K1F divided by K1R, concentration NO squared, concentration O2. And that is my overall rate law. And so what we can see is we can overall get the order, NO is second order, O2 is first order. When you're dealing with an overall rate law, when you have really high orders like this across the board, that's generally indicative of the fact that you have a later step that is probably slow. You're needing to have multiple collisions happen in order to get this, in order to get it through to the end. But just because the overall rate law is NO2 to the second and O2 to the first, doesn't mean you have a single collision of two NO molecules and an O2 molecule. It's not a single collision, it's really two sequential collisions, two sequential steps that have to occur. It is worth noting that you could also write this. You'll note that those are all numbers, those are all Ks. And so you could easily write this as just rate is equal to K overall times the concentration of NO squared, concentration of N2, and you come up with this relationship that K for the overall rate is equal to K2, K1 forward, divided by K1 reverse. And so this gives you a little more information. You can kind of decompose the different aspects of the rate constant. So this overall rate constant, if you did say, some initial rate method or some Arrhenius work or anything like that to obtain what the value for K is, it's really composed of these three different values. And so if we want to think about modifying or controlling the reaction kinetics, there's really multiple parts here, right? The bigger K, is K2, that's a forward rate constant, K1 forward, so the bigger these values are, the faster your forward rates are, the faster the overall reaction happens. If that reverse rate is fast, K1 reverse is large, the overall rate constant will be smaller because you'd be dividing by that number, which makes sense. That moving forward, the faster you move forward through reactions, the more rapidly they happen, whereas that reverse, if you're going backwards a lot, if this intermediate is very short-lived, it keeps falling apart really quickly, then it's unlikely that your overall rate would be very quick. Participation 918, question 3. Consider the following reaction mechanism. Step 1, A plus B goes to C, and 2, C plus B goes to D. What will the overall rate law be if the first step is slow? This is the third question on participation 918, due Friday, September 18th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, consider the following reaction mechanism. This one, what will the overall rate law be if the first step is slow? Another participation question. I don't think we're going to maintain this pace through the rest of the set of videos, but who knows? Maybe we will. We're over halfway through, so got a couple of videos left in chapter 12. See you there.